Okay, we're going to get started now. I'm Pat Hindle from Microwave Journal. I'd like to welcome everybody to the 5G Massive MIMO panel session. As you can see all day long, this room has been pretty full with 5G activities, great presentations so far. So as the first deployments for 5G mobile will encompass wider bandwidths, higher orders of carrier aggregation, and MIMO, and this will increase the data rates and capacity. However, as we move from MIMO to massive MIMO, there's a lot of challenges that we face, increasing power, cost, and size. So we have to address those challenges in order to be able to deploy it. So we have some experts here who will address those challenges, and we will take questions from the audience. So please think about getting questions and raise your hand when we get to that point, and I'll bring the microphone to you. So we have a few representatives from Test and Measurement, Keysight, Rohde & Schwartz, and National Instruments. Then we have representatives from the semiconductor industry, from Global Foundries and MACOM. And finally, from the systems point of view, we have someone from China Mobile here. So I'll let everybody each person could introduce themselves and then what challenges your company is seeing in massive MIMO deployment and how you're addressing those challenges. Each one of you can give a few minutes on that. That would be great. We'll start with Blair and Lee.
Hello everyone, good afternoon, and I'm Barry from Keysight. My Chinese name is Feng, maybe some of you know me. I'm very glad here to discuss the 5G and massive MIMO test challenges and some maybe solutions for you, for industry. And from Keysight, we are focused on the next generation 5G test and measurement, especially the 5G new radio. We all know that the 3GPP have released the standard physical layer. Most of the physical layer standard has released. And we have very clear about the numerology and physical channels or definitions. So most of the industry have changed from original years from the research to current status. Maybe the product, the commercial product. So test measurement the requirement has changed from the research to most of our test. So currently our test is focused on the 3GPP standard, and for massive MIMO. Is new because in 4G, in LT, there is less test requirement for MIMO. But in 5G, because the massive MIMO or beamforming is the standard in the equipment, in the base station and mobile. So MIMO and beamforming measurement will be very key test items in 5G new radio. But in before, we just measured some the size of our specifications for the base station. But currently, we have to measure the MIMO, EVM, or MIMO, or beamforming phase and amplitude between the different branches. So that will be the new test and measurement requirements for 5G. And in before. Prototyping phase, there is no very critical test certification requirement for maybe UVM or some ARC test. But when we test according to the healthy standard, 3DG standard, that will be more critical or test requirement for the accuracy and the dynamic range for the test. So we have to use the high performance test instrument to fulfill the test requirements. So that will be also the challenge for the massive MIMO. So the traditional single channel instruments like single generators and spectral analyzers maybe have more challenges to test 5G massive MIMO equipment. We not only need more channels, multi-channels to cover MIMO test and beamforming test. We also need high performance or high accurate test specifications with this instrument to match the standard requirement. So that will be key challenges to instrument also for our customers. That will be the point from PSAT for 5G massive MIMO test.
Okay, Randall. Okay, thank you. My name is Tony Guo from Schwartz. I'm now in the strategic business development manager for 5G in Schwartz, China. Come back to the topic today, massive MIMO. I think Schwartz is a test, like PISA, we are the test environment vendors. Therefore, we're talking about more about how to test MIMO issues with our main topic. I think the 5G, there's like described, there are several new technologies for 5G to enhance the 5G performance. For example, the EMBB case, we will use massive MIMO as one of the technology. Another technology is millimeter wave to increase the bandwidth, to increase the data rate. So for the 5G massive MIMO base station, for example, if we test, for example, if in millimeter wave, no more there's cable connection. Therefore, OTA test will be very important to evaluate the performance of the MIMO system. So even come back to the sub-6 bands for 5G application, also the OTA test we think is very important. Therefore, today in the morning session, I think many the keynote speakers, they also talking about this. Schwartz in mobile World Mobile Congress Barcelona this year, we announced a new test solution called PWC, planar wave converter test solution for the massive MIMO OTA test solution for the base station. Apparently, Schwartz also supply have the solution for we have a chamber which can be used. There's 10 table inside, which can be used for the OTA, the UE, the 5G UE OTA test solution. If you have interest, you can have a full discussion offline. Thank you.
Anyone? Okay, good afternoon. My name is Manuel Lum. I'm the Director of Marketing for the Software Defined Radio portfolio at National Instruments. So we were introduced as a test and measurement company. That may be how many of you know National Instruments, but you may not be aware that we actually do a lot of research using our software-defined radio technology at the very front end of the standards being developed. And so through our lead user program, we've actually been working on 5G, massive MIMO, millimeter wave, many other examples, since 2010. And so all our software-defined radio equipment has been used in some of the biggest massive MIMO trials, things with places like Lund and Bristol University, where they've achieved records for spectral efficiency. We've also been working with some key industry partners like Intel, Facebook, and Samsung. And what we find is being at that very front bleeding edge of the research that goes into those types of standards and also participating in 3GPP gives us a very intimate understanding of the issues and the problems of being able to develop, just the very focused enabling technology for things like massive MIMO, but then also understanding the issues related to how do we commercialize it, how do we make these things economical enough, small enough, consume a lot less power. And then, of course, we take that and we parlay that on the test side, where you have to now test all these systems. And so we develop the knowledge at the very start, and then we use it to actually come up with test systems that will allow us to help our customers test massive MIMO. I think, as my colleagues have said, massive MIMO brings many different challenges. Trying to do over-the-air testing is challenging, it's expensive, and so we continue to look with the rest of industry on how we can do this more economically. There are trade-offs, of course, with more antennas. You can get, for example, lower power per antenna element. Maybe the quality per element doesn't need to be quite as good, but at a system level, how do you test that? And it probably needs to be over-the-air testing, at least for the immediate future. So these are all challenges that we look forward to solving with our industry partners and academic partners. Thank you.
Okay, Peter?
Good afternoon. My name is Peter Rabetti. I'm the Senior Director of Business Development and Product Line Management at Global Foundries. And I'd say our journey with 5G and massive MIMO in general probably started 3-4 years ago. And being at the technology level, as a foundry provider, really our focus was trying to understand what are some of the key requirements that are going to drive technology choice when it comes to developing systems for 5G and massive MIMO. And I think back then the specs were very, very unclear, obviously, and as they've matured and developed over time, we've learned more from both our customers and from what's been discussed and ratified by the 3GPP and the various standards bodies. As we learn, we develop solutions based upon that learning and leverage the technologies and the know-how that we have within Global Foundries to come up with not just a silicon technology, but a total solution that a customer can be able to take examples that we do as part of what we call our RF pathfinding work, where we develop circuits, develop representative benchmarking that customers can use and leverage in their own developments and give them guidance as it relates to picking a particular technology and even picking a particular approach in leveraging that technology. I think what has happened is that a lot of that learning, and as we develop the specs around our technologies, I think some of the key challenges that we find as we sit here, at least from the technology perspective at Global Foundries, is being able to provide very efficient power, particularly for the UE case when we're talking about millimeter wave. Really providing efficient power such that these devices can last on a battery for some reasonable amount of time. And that really drives a particular technology choice when it comes to, a set of technology choices and approaches when it comes to that type of development. As we've progressed, and it's actually going to be something that's going to be announced today as part of a press release, one of the things that we've done at Global Foundries is working to develop an ecosystem for our customers that can help them depend and work with some of our partners, folks like Keysight and others that may be part of the ecosystem that allows them to leverage the learning around test, leverage learning around design, leverage learning around packaging, and other aspects of design that are going to be very important as it comes to developing systems for 5G and massive MIMO. Thank you.
Into data converters and optics. So we're looking at the ecosystem of a complete base station design, both sub-6 and millimeter wave, that takes RF to light in front of the baseband unit, and how we can bring an integrated technology portfolio together to help with power consumption, affordability, and a dynamic set of design choices to allow a different set of base station designs to be realized with very similar technology, almost a frequency agnostic architecture. So we're working to bring these pieces together in a higher level of integration to fundamentally try to bring a very affordable product to drive the cost of base stations down and certainly bring the power consumption down of those base stations. So we're looking at many different aspects, from what I call a software-defined antenna versus a software-defined radio, the same basic principles, and then working through some of our experience in the radar world to bring in how to test and how to satisfy the 3GPP requirements. But as components, not as a base station in itself, but using the base station as our test platform.
Good afternoon. I'm Zhiming Fan from China Mobile, and I'm the project manager mainly focused on the 5G trials and the key technology validation in China Mobile. And as we all know, for the massive MIMO is a very important technology for the 5G because it could increase the spectrum efficiency to satisfy the throughput of 5G requirements. And on the other hand, it can also guarantee a very high coverage for the 5G base station. As you all know, for the 5G frequency band, it is much more higher than the 4G. So the freedom loss is very high. So we need more ERP to guarantee from our operators to guarantee the coverage. And from China Mobile's perspective, we think our needs is that, as we all know, 5G network will be commercialized before 2020. And in this year, we will begin our large-scale trial in 5 cities, mainly for the sub-6 gigahertz, and how to make our network, how to decrease the cost and make it much more economically for our network is very important for us. And on the other hand, for the millimeter waves, we think there are a lot of key technologies need to research, including the architecture and device and some test or measurements technologies. For China Mobile, we have do a lot. We also have do a lot in this field. For example, we have organized our China Mobile Innovation Lab, including different work groups to mainly for the challenges for the key technology in 5G. And we also organized the O-Run Alliance in this year MWC to try to find some solutions to decrease the cost of the networks. And I'm very glad to be here to discuss these challenges with the whole industry here to find some good solutions for the 5G network deployment. Thank you.
Then I'll keep going. But if you have any questions, just raise your hand and I'll pass you the microphone. So let's talk to the semiconductor guys. What specifically are you guys using? What techniques can you suggest to greatly reduce the power consumption at the RF front end level? And maybe Peter and Tony could take a stab at that.
We really think that silicon is the key choice in terms of development and integration. for these front-end module beamformers.
And is that mainly for an integration?
Yeah, mainly for integration, but also the ability to integrate logic and control, whether it's for digital beamforming or some type of variation on a hybrid type of architecture. We really believe that silicon is the choice, and more specifically, we really think that SOI, particularly as it relates to integration, is the choice. And there's several reasons for that. One, as we get into these systems where you need to be able to dynamically control the performance of the radio for a given situation, whether you need high output power in a given situation or low leakage in another given situation. Technologies like FDSOI have that capability to be able to use things like backgate bias control to be able to dynamically control the performance of the transistor. Throttle it one way for performance and throttle it the other for improved leakage. And we believe having that dynamic ability, having that capability in the technology is going to be really important in terms of optimizing these systems in the long run to get the lowest power, not only device, but lowest power network in order to service customers.
Tony?
So we've taken a slightly different approach. We're primarily looking again on silicon as our base for our FEM modules, and then higher level of integration there with more of a 3D stacked integration, using the benefits of the silicon on one side and the benefits of the GaN on the other side for power, where we can do a higher level of integration and bring the ADB converters up to the aperture, to the antenna, to provide that high level of integration with a lot of efficiency that comes with that. In addition to that, we're also bringing our silicon photonics technology in to the back end for the optics piece, where we can eliminate some of the throughput issues that are in the antenna with the SerDes block that comes in, and eliminate that as well. So we're able to, again, bring these two halves together and pull a lot of the roadblocks that you have within the antenna. And this primarily for a phased array that's doing multi-beam MIMO, where ultimately you want to be in terms of the technology. As it moves over into millimeter wave, we feel that that's the higher level of integration that's required here to bring that affordability piece in.
Okay, and then on the test and measurement side, what specific solutions are you guys bringing to market that will reduce the cost and still be able to verify, hundreds of antennas in a not only cost but also test time?
This one side, we just mentioned we launched sub-6 TWC N-wave converter test solution. For the missing MIMO antenna test, the far field OTA test is the final evaluation method, the best one. But problem is if we test in far field for the base station antenna, for example, it's 1 meter high, and you can calculate the far field in some frequency would be a very large anode chamber will be needed. This is very high cost. Therefore, the final test we are looking for to lower the test cost by using of either the compact field test method or the near field test method. Run-Schwarz now we propose to use the planar wave converter test method. If you use the near field test method, you have to have software to convert the near field test result to the far field result finally, both for the transmission and the receiving result. By using of the planar wave converter method, which means it's a hardware converter, we can use of this just For example, if 1 meter antenna array, we can have the distance from the converter to the DUT about 1.5 meter. We can generate about 1 meter quasi size, which can largely reduce the test chamber size. This can be used for very easily to test for or convenient test for the business for the base station development.
Daniel and Blair?
Yeah, I'd say, excuse me, we've done a lot of research on the analog and the digital side. I think you covered the analog side well. On the digital side, I have some of the same comments as some of the semiconductor colleagues here, and being formerly from Xilinx, I also have a lot of background on the digital side. And silicon, I think, is the answer there as well. On the baseband side, you're seeing integration through SoCs, and that's everywhere from the UE side with companies like Qualcomm, of course, that everyone knows well. But even on the E-Node B side and the G-Node B side going into 5G, there's a lot more development around ASICs, which are essentially system on chip combining multiple heterogeneous processors with hardware accelerators. And as that technology continues to go and kind of march down Moore's law to an extent, and more towards more and more integration, that's where you see both the cost savings, but especially the power savings. One of the biggest consumers of power in the overall system level is just moving all that analog data to digital and then around the digital subsystem. And with more integration, if you can remove all those JESD links on MGTs, which burn a lot of power, you can also save a lot of power. And then having the right means to test that silicon then, and we have semiconductor test solutions within NI, where we work with a lot of those companies that you would expect. That's where we see a lot of the savings that will come in terms of actually getting massive MIMO systems rolled out into production.
High cost or to increase the cost, but maybe it's from different aspect. Maybe most of things that it comes from the increasing the number of channels, the RF channels and baseband channels. But in fact, maybe more important, it comes from the complexity of the system. Because the channel, we normally to ensure the RF performance for each single channel, but also we have to calibrate the whole system, the phase and amplitude coherence from the different channels. We also need to calibrate the wideband performance, wideband maybe linear distortion or unlinear distortion from all the channels. So that will give high complexity to the whole system. The customer, the designing engineer or a development engineer have to invest more time or equipment on test and troubleshooting on this complexity of the system. So we have released many more diversity instrument test measurement solutions to decrease the complexity of this system. We have different kind of system for these calibrations, maybe for beamforming and multi-channel calibration for different kind of different kind of parts of the maybe base station or also the phones, maybe like phase array antenna calibration and multi-channels, RF channels calibration, and also we have new wideband distortion calibration method using a metrology level calibrator from the similar like used in the network analyzers. We also used a multi-channel instrument like multi-channel signal generators and analyzers to simultaneous to test multi-channel the downlink and uplink signals. So we also have systems to integrate the interface, maybe interface directly to 64 or 128 or 256 antenna system or RU systems, and also switch to modular instruments to increase the test efficiency. We also have OTA method that will be maybe covered by another colleague in Thursday panel. So for conducted measurement, we are planning to use the different multi-channel measurement or calibration or network analyzer solutions to cover the different kinds of issues or complexity issues in massive MIMO system development and test and measurement. So I think that will be extremely to decrease the complexity and the cost of the customers.
Okay, maybe from a China Mobile perspective, what is the main challenge that you're facing to field a system that these guys can help you with, and we'll have them maybe answer your question.
The massive MIMO challenges we can have several aspects for this. First is for the network levels. We need much more analysis or research on how to organize the network. For example, in some hotspot areas, we can use the massive MIMO with much more antennas or digital channels to guarantee the traffic density, high traffic density. But in some area in which maybe the traffic density is not very high, we can decrease the element numbers or the digital channels so that to decrease the power consumption or the cost. This is for the network levels. And on the other hand, for the system levels, for the subsystem speakers, I think the digital beamforming is the mainstream architecture. But for the millimeter waves, as we have discussed, we have seen before, maybe the hybrid architecture is the mainstream because the low cost it could decrease the digital channel numbers and also can guarantee a very high regain. And on the other hand, I think some algorithms, for example, the DPD, the linearization technologies is also needs much more research to improve the PA efficiency so that to decrease the power consumption. And also some calibration technologies and some other heat dissipation technologies could be used to decrease the waves, the power consumption. And on the other hand, we think the semiconductor aspect also very important. As you all know, maybe for the sub-6 gigahertz, the device is more material. But for the millimeter waves, especially for the national device, it's not very material, especially for the active devices such as the PAs or some transceivers. Maybe we need much more do much more work on the semiconductor material and some new materials such as the gun to improve the PA efficiency. So that should guarantee such massive MIMOs with low cost and low power consumption.
Okay, any questions from the audience? Anybody?
This is Jill from Covestro. We are a material suppliers globally, number one for the polycarbonate. I'm not sure I have the right question to the expert, but try to get more information from you. As an expert from China Mobile just mentioned a lot of cost. So from your discussion, you mentioned about the systems, testing, a lot. Do you think installation and also maintenance cost would also be a key for the total cost system?
As I understand, I think for the maintenance cost is also be a very has a very important very large portion in the high total cost. As you all know that for the massive MIMO, the power consumption is very high, so it will use a lot of electricity for the maintenance. As our China Mobiles, we are trying to do a lot of work to make the base station more power efficient to decrease the electricity, because we have seen that it has been a very high cost for us.
The maintenance and installation cost is important. Do you think the weight reduction for the antenna would be one of the topic for the 5G? Weight reduction of the antenna.
The heat dissipation has a very high portion for the whole heat, and also some for the sub-6 gigahertz, some inactive components such as filters also is very large. It has a very heat, but I'm not very sure the antenna. The weight of the antenna is a very high portion for the RU. From my understanding, I think the main component is the heat dissipation and some inactive components.
Okay, the metal materials, right? Okay, thank you.
Okay, we only got another minute. Last words, real quick. Who's going to field the first true massive MIMO system? What's the approximate configuration, like number of elements, frequency, and just real quick, go down the line. Where you see people who have the most advanced systems.
Systems are out. The systems are going out there. They're being deployed. I can't say what number of elements it is, but we've got customers already in play that are developing products and going to market.
Anybody else?
Yeah, we also have customers that are ready to go out for their initial deployment for trials in their 5G arena today.
Yeah, I'll be interested to see how fast it really ramps up in terms of production deployment. But we do have a customer that we worked with at the University of Bristol several years ago that set the speed record with a massive MIMO 128 antenna system, 145 bits per second per hertz, which is still, I think, the spectral efficiency record right now. Getting that into production, I think, is going to be a really big challenge. And 128 antennas is not a simple problem to solve, but I think the technology is certainly trending that way, and we'll get there. It's a matter of time.
Okay, and as we alluded to earlier, there is another 5G panel on Thursday. It's 11:40. You'll be in this room on Thursday, and we'll be addressing 5G millimeter wave OTA testing. So we hope to see everybody back here, and thank you for joining us.